Okay, we are going to take a look at our organic chemistry practice diploma questions. So again, I'm going to go through these solutions. If you need to skip to a different question or anything like that, you can do so now. But otherwise, I'm just going to go through them sort of simply to make sure that we're all on the same page for these practice diploma questions. So let's take a look with question number 21. It says the molecular formula for 2,5-dimethyl cyclohexane 1-ol is blank. Now, because we're counting essentially the number of of C's and H's and O's, we're just going to simply write out the structure and count how many of each we have. So this is cyclohexane 1-ol. So I'm going to start with cyclohex, so that would be carbon. I'm going to give lots of room here. I'm going to give myself lots of room. So I have carbon. So I have a 6-sided carbon ring. And off my first carbon, let's just call this the top carbon. I have an OH group because it's an alcohol. So let's actually just do this in a new color, and then that way we can keep track of everything that we've done. So we've taken care of the fact that this is an alcohol. We've taken care of the fact that this is a hex, okay, and it's cyclohex, so it's all together. And then we have 2,5-dimethyl. So we have 2,5-dimethyl. I'll do this in green so we can see this. So off our second, we have a methyl group. 3, 4, and off our fifth, we have another methyl group. Okay, and then we also have to add in our hydrogens in any place that we do not have another functional group coming off of it. So if we take a look, we have each carbon should have 4 bonds. So this guy will have an extra hydrogen, and I'm going to do this in orange to make sure we can keep track. We have 1, another one here, then we have 2 off of these guys, 1 off of this guy, and 2 off of these guys. So when we count, we should have 4 bonds for each carbon, 1 bond for each hydrogen, and 2 bonds for an oxygen. So when I go to count, I have 1, 2, 3, 4, 5, 6, 7, 8 carbons, so I can cancel out the top 2 answers as being a possibility. So I have 8 carbons. All right, I have 1 oxygen, which is consistent in both, and now I just need to count my hydrogens. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So our correct answer here is D. All right, now again, I would recommend that in this case, our simplest way to do this is to draw this out so that we don't lose track of any of our hydrogens or carbons or anything like that that would be present. All right, let's take a look at the next question. Question number 22 says butanoic acid can be described as a blank compound, and the functional group in butanoic acid is blank. Now, this information, there's a little bit to take a look at. First of all, we're answering 2 questions with this information, so that is important. All right, and when we take a look at the question, it says butanoic acid can be described as a blank compound. Well, let's take a look at our fill in the blank portion. We either have aromatic or aliphatic. Well, aromatic, if it's butanoic acid, in order for a compound to be aromatic, it has to have a benzene ring. Now, because butanoic acid doesn't say benzene and it doesn't say phenyl, we can cross out B and A as possible example because it is an aliphatic compound. Okay, the other thing to take a look at, it says the functional group in butanoic acid is blank. Okay, so we have either a carboxyl group or an ester group. Now, because we have a carboxylic acid, hence the name oic acid, our answer here is C. Okay, we have an aliphatic carboxylic acid. Okay, so that's not too hard, as long as you know that the ending oic acid, okay, oic acid is in fact a carboxylic acid. Okay, then this question here, we have, says listed in order from the acid that has the lowest boiling point to the acid that has the highest boiling point. Okay, in these 4 things listed up above, which is the order here for that. So the lowest boiling point to the highest boiling point based on the 4 entities listed in that box at the top. So when we take a look at that, generally our highest boiling point is something that is a long chain. Long chain. High boiling point, long chain. Small chain is over here. So, based on what we see in this example here, okay, we see based on the number of carbons, they all seem to be a carboxylic acid, and based on the number of carbons, this guy at the bottom is the longest. Okay, then we have our octanoic acid after that as the second longest, then probably butanoic acid and methanoic acid. So how do I know that? Let's take a look. Here I have 16 carbons that are CH2 plus my terminal carbon here and another terminal carbon here. So this is actually 18 carbons long. Okay, octanoic acid is 8 carbons long. Methanoic acid is 1 carbon long. And bute, it looks like there's C3 and a 1, so that means that we have 4 carbons. Now again, you should know based on the name that we have 4, 1, 8, and maybe you don't know what octadecanoic acid is, but we can count based on this entity here that we have 18 carbons. So our highest boiling point is going to be our 4, 3, 1, and 2. So we have 2, 1, 3, 4 as our order. And that is simply based on the chain length. So that is another important thing to take a look at. All right, let's take a look at the next question here. This says the 4 molecules listed above that are isomers of C5H10 are numbered blank. Okay, let's draw out C5H10 and see what we get and see the type of, or see which one of these has 5 carbons and 10 hydrogens. That might be the best way to do this. So, pent-2-ene, whoopsies, pent-2-ene looks something like this. Pent, 1, 2, 3, 4, 5, pent, 1, 2, 2-ene. Okay, this means that I have 1, 2, 3. So if I count each ticky as a hydrogen, I would get C5H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I get 10. So C5H10, that is in fact one of our isomers that we have here. Pent-2-ine, I'll kind of alternate colors here. Pent-2-ine, 1, 2, 3, 4, 5. This guy has 3 bonds. This is 1, 2, 3. So again, if I count, I have C5. And there's a few ways to go about this. I can count here, so I can go 1, 2, 3, 4, 5, 6, 7, 8. However, I knew that because pent-2-ene did work, pent-2-ine won't work because a triple bond here steals away 2 bonds, one from this carbon and one from this carbon. So because of that, that takes away 2 hydrogens. And that's because those electrons are now shared in between those carbons. So that is something to look out for. So 2 definitely is not. Cyclopentane. Let's take a look at cyclopentane. Again, we have 1. Oops, I'm going to do this in this color. 1, 2, 3, 4. Oops, that is crazy. 5. This is kind of a crazy diagram here. So I have 5 carbons, and then each carbon is going to have a hydrogen, meaning that this is also going to be C5H10. So 3 is also a possible choice here. Then we have methyl propane. Methyl propane. Well, methyl propane, I'm going to look at that and say right away, if I only have one methyl group on a prop, that means there's only going to be 4 carbons total. So I'm just going to put a line right through one. That one doesn't even make sense to try. Now, pardon me, if I take a look at dimethyl propane, well, that could be something to take a look at. So dimethyl propane, prop meaning 1, 2, 3. Dimethyl has to be off our center carbon. So when I take a look, I have C5H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So C5H12. So that guy is no good there. Let's take a look at the next one, though. Ethyl cyclopropane. Ethyl cyclopropane. So we have cyclo. So we have 1, 2, 3. And we have an ethyl group coming off. And then we need to make sure that each of these carbons has hydrogens filled in. So each carbon looks like it has 4 bonds. So this is C5H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C5H10. So here's another one. Oops. That is a number 10. So ethyl cyclopropane does work. Now, since we need 4 blanks, I'm going to assume, I will never assume, but I should, that number 7 is going to be our other blank. But let's just take a look just to double check that we haven't made a mistake on one of our other drawings here. So methyl cyclobutane. Cyclobutane looks something like this. And we have a methyl group coming off of one of these carbons. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right here? Yep. So I have C5, and I have 3, 4, 5, 6, 7, 8, 9, 10. So C5H10, 7 is our other answer. So our values listed in any order as per the diploma is, I always like to do numerical 1, 3, 6, and 7. Okay. Take a look at the next question. So this question says the structures and descriptions that apply to methyl cyclopropane, methyl cyclopentane, are numbered above. Okay, a few things that you might want to do. You may want to draw methyl cyclopentane. So I'm going to draw it to the side here. Now my drawings are never quite perfect, so sorry about that. They're never quite awesome like the computer graphics are. But we have methyl, we have our 1 methyl group coming off of our cyclopropane. Now this is my what it looks like here, my group, and we can methyl cyclopentane. I need to stop saying propane. This is what we have here, and we can then go through and pick out anything that looks like this diagram or anything that belongs. Okay, well, when I take a look, I definitely see that number 2 matches the diagram that I just drew. I know that 3 and 1 are no-goes. Okay, I also know that this is a branched, because I have my methyl group coming off of it, so it's a branched hydrocarbon. It's not unbranched because we just said it was branched. Okay, is it saturated? Well, it is. We have it fully saturated any place that we can. We don't have any extra bonds in being shared between carbons. It is saturated with as many hydrogens as we can. So that means it's not unsaturated. And it also doesn't have any double bonds. If it had double bonds, we would call it unsaturated. So in this case, we have 2, 4, 6, and 8 in any order. So 2, 4, 6, 8. Again, I like to write these in numerical order. It makes life a little bit easier for your brain and for everyone else marking it, things like that. So again, I can cross out number 1. I drew my methyl cyclopentane. Please draw it. It does save you some hassle when you're talking about it. Okay, no double bonds, so I can cross out number 9. It has no double or triple bonds again, so I can cross out 7, giving me 8 and 6. It's branched, so I can cross out unbranched. It is number 4 and number 2. Perfect. Let's take a look at 23. This one says, a mixture of liquid methanol and liquid ethanol can be separated by blank. And the physical characteristic, of these compounds that allows the separation is blank. So when we take a look at this question, we can get an idea of what this is talking about when we talk about either precipitation or fractional distillation. So let's start with that. It says we can separate these two things by a certain process. Now, precipitation is pulling it out using some sort of reaction. Usually it's a double or single replacement reaction. So precipitation doesn't really sound too consistent with what we have done in organic chemistry. However, we know from our lesson on separating organic compounds in refineries, we know that fractional distillation is a process where we have separation of organics, and it can be liquids or gases that separate at different heats, using different heats, which is all to do with boiling point. So by knowing what fractional distillation is, we actually answered the second part, and that is B. So we have fractional distillation and our boiling point that allows us to separate those two entities using a boiling point. Okay, let's take a look at the next one. So zoom in here. This gives us an equation up here. We have C2H4. Now I like to draw it out. I'm a visual person. I like to see what's going on. So I have C2H4, which means that I have a double bond in the middle here. So I have ethene. And when I have a plus sign and I have a halogen, I'm guessing I am going to undergo some sort of addition reaction. Now, generally what I would expect is that if I have my bromine, which is Br2, like this, I'm going to break this bond here and add my bromine in an addition reaction. Now, that's just a hunch as to what this question is asking, but let's take a look. It says the reactants above undergo a blank reaction. Well, we just said an addition reaction. I'm going to cross A and B right out, get them out of my head. Okay, and the product of the reaction is blank, or 1,2-dibromo. And now, since we know that we broke this bond, our product is going to be we're going to get 2 bromines added in, and the rest of them are hydrogens. Now, since, again, we broke one of the bonds in between the 2 carbons, we no longer have a double bond, so it's not an alkene, it's an alkane. Since we have an alkane, we're dealing with C as the correct answer. So it's ethane. Let's take a look at another example here. It says use the following information to answer the next question. We have ethene can be described as both a blank compound and a blank molecule. So we have ethene is a plant hormone that causes fruits and vegetables to ripen. Ethene can be produced artificially by the reaction represented by the following equation. So it looks like ethanol is given in a catalyst, and this is some sort of elimination reaction. We have water eliminated. Sometimes we call it a condensation reaction. Okay, and what we expect is that this is an aliphatic molecule. Now, again, the only way something can be aromatic is if it has a benzene ring in it. Now, since this doesn't have a benzene in it, we can immediately cross out both C and D because they are not possible answers. But when we take a look between our A and our B, we see that we have an aliphatic as our first blank, which is correct, and ethene is it's not saturated. We don't have as many hydrogens as we possibly can, so this is an unsaturated compound. Again, that is all to do with the fact that we have a double bond. So again, if we see a double bond or a triple bond, we know that it's unsaturated compound. All right. So, question number 26, it says, the production of propan-2-ol from propene is a blank reaction. Propan-2-ol is likely to be blank in water. So, one thing we can take a look at here. So, let's look at the reaction type first. That's probably the easiest. Again, I would suggest drawing this compound out as a structural formula so that we can see that they are consistent between our first and our initial reactants in our product. So when we take a look, we have propene, which looks something like this. Okay, we have propene, like so. We mix it with water, and we get our bond broken, okay, and we get water added into our product. So I would call this an addition reaction. Okay, so we're adding water into our compound. Now, I also know, based on my studying and things like that, then the formation of an alcohol can be done through the addition of water to an alkene. So I know that. So, because I know that this is likely an addition reaction, like I mentioned, and I'm going to just cross out substitution as a possible answer. Okay, then propan-2-ol is likely to be blank in water. Well, since propan-2-ol, most alcohols, because they do have this hydroxyl group, most alcohols, as a general rule, are soluble in water. However, if I'm unsure, I also know that our polar substances, which this is, there is a slight pole on this side of a negative dipole on this side of our compound, meaning that there is a polar molecule. Now, because this is polar molecule, polar solvents dissolve polar molecules, so that means that this is going to be soluble in water. Okay, again, solubility is all to do with polarity and symmetry of a molecule. So, 27 says, which of the following rows identifies a reactant and its product in a polymerization reaction? Now remember, polymerization reaction is the addition of multiple monomers. So if we have ethene, we should get polyethene or polyethylene. And if we have propene, we should get polypropene. So the only reaction that I see in this list given that would make sense is our ethene and our polyethene. But we can double check. Reactant and product doesn't really make sense to have the same reactant and product. Even if you are unsure about this question, you can cross that out. That doesn't really make sense. Okay, if I start with propene, I'm pretty certain that B is the correct answer, but we'll go through. So if I look at propene to ethene, well, all I've done is I've lost a carbon branch off of my chain. So really that's not polymerization. I'm not adding a bunch of the same components, the same entity, in to make a polymer. Okay, so I'm going to cross C out. Propene to polyethene. Well, this is closer, but if I had polypropene, it should be polypropene. If I have many propes, it's poly. So because I don't have many propes, I have many eths, then I have ethene and polyethene, or one as my monomer and many as my polymer. So B is the only sort of good answer given there. Okay, one more here. So this says, esters with pleasant odors and flavors are often used as food additives. An ester that is used for fruity apple flavor is shown below. The ester shown above could be produced by the reaction of blank and blank. So it has our carboxylic acid and our alcohol. Now, because we have a carboxylic acid and an ethanol, we know that those are the two reactants that we need to form an ester. So we know that our parent chain, or what I like to call the parent chain, is our carboxylic acid, and the branch is our alcohol. So when we take a look, I'm going to count the number of carbons in my parent chain, which is going to be my carboxylic acid, and then I'm going to count the numbers in my alcohol to count how many are in that sort of branch. So I have 1, 2, 3, 4, 5. So I have 5 carbons, meaning that it's pentanoic acid. is my first one. So I'm going to cross out these. And again, I know that because the parent branch, starts with this double bonded O on it. And because that double bonded O is the main portion of your ester, we call that the parent branch. So our parent branch is that whole long chain being pentanoic acid. Now when I go to count my carbons in my alcohol, I see that I have 2 carbons. So because I have 2 carbons, I have ethanol. So my correct answer here is pentanoic acid and ethanol forming my ester. Okay, so that's it for our questions on our organic chemistry practice diploma. There's lots and lots of examples to go through either in a textbook or found online, and that's a very good idea to go through the style of questions that are a little bit more complex, require you to apply your knowledge. Those are good questions to take a look at. So I would suggest doing some of those right now, and good luck.